Hello, Andy Schweitzer here. This is a short video on one of our first ideas of kinetics, and I'm going to label this particular video as being concentration versus initial rate. So, a couple objectives, or basically what we want to get done with this video is all right. First topic is when you start a reaction. So what does initial mean? Initial rate. Okay. We've already talked about the collision theory, and when I talk about initial rate, essentially means that, okay, if I take a beaker A and I take beaker B, all right, plug them in here, and I dump B into A, and all of a sudden these things start to react. As soon as you start having collisions of A and B, right, let's say they produce, hypothetically, C. As soon as these collisions start, okay, the reaction is basically at its optimal point as far as speed is concerned. Just about every single reaction depends on how it sets up, but if you were to track the concentration of one of these items, let's just say we're checking A, let's check C, a product, and let's go versus time. Okay, so immediately at the bottom there is no C. But as we produce it, the reactions, there's lots of A's, lots of B's, and they're colliding at a very high frequency, relatively speaking. So my rate picks up, and as soon as A and B start colliding, they start to essentially be removed from the system, and the reaction starts to dwindle, and it looks like this. And eventually it flattens out. So this initial point here is called the initial rate. Now, in order to figure out the actual rate at times beyond the initial moments of the reaction, then we would need to use calculus. All right, in order to figure out, okay, what is the rate at, say, at this point right here, and that's going to be at the next video. Now, the actual calculus of it, the derivation of the mathematical expressions in order to determine the rate at times t, that is not really of any concern for us on advanced placement chemistry. The idea is to be able to use it, to understand the concepts behind it, to be able to use the equations. Okay. Now, at this point, we are going to be looking at the initial rate. Now, the initial rate, how do we calculate it? So, one, we want to know what is the initial rate and why is it important. Kind of talked about that just now. And two would be, okay, how do we calculate it, or, how do we calculate this thing? For this, we use what's called a rate law expression. Okay. Now, a rate law expression essentially looks like this. You have your rate, okay, equals, and then you have an equilibrium constant, a rate constant. Okay, so this is the actual rate, and the rate's going to be in something, question mark, per time. So it's going to be in some rate. This is a constant, and this, and then here we would simply line up our reactants. Every reactant that you'd have would go here, and it would be the concentration of these reactants. Okay. Then here up top we put our orders, and we'll explain what order means in a second. But with this mathematical expression, if you knew your initial concentrations, say X and Y, or for this particular chemical reaction, it would be A and B. We'd have 1 for A and 1 for B. If we then knew our rate constant K, we could figure out our rate. Or if you knew the rate, so basically we have 1, 2, 3, 4 variables here. If you knew 3 of the 4, you could find the fourth one. Pretty simple algebra at this point, just dividing out. So for this particular PowerPoint, our really strong objective here would be to do a couple of things with this rate law expression. Okay. Now, I'm going to put on here for an objective might be, okay, what is going to be an order? Okay. Now, I will explain what the orders are, and we'll know that, but as far as things in action or something we want to be able to achieve in this chapter, that's sort of a cog in the machine. Okay, it tells you what this is, but it doesn't really explain what we want to be able to figure out for this particular chemical reaction. So there are a couple of things they actually want you to be able to do. Okay, and one might be, okay, calculate a rate, and it would only be initial rate. We want to be able to calculate the orders. Okay, those are things that I'm going to look at here. Okay, and we want to be able to calculate K. So those are the variables we'd want to be able to find. So they're going to set up for you various types of problems that are going to ask you to do these things. Okay. So our first thing here, now I would also say that in this chapter there are 3 PowerPoints, and they're pretty good PowerPoints in the sense that a lot of this stuff is just mathematics, and you just need to be walked through and kind of exposed to these concepts, and the questions that surround them are usually pretty straightforward if you understand these simpler concepts. Now, the mathematics behind it can be more complicated, but like I said, the questions associated with them generally are pretty easy. Okay? So now, and I have the PowerPoint up here, and I will be flashing between it. This is just one of them that I will look at here. Okay, and I'll flash back and forth between just doing some examples and how this works. Okay, so first thing is orders. Now we have commonly what's referred to as a zero order. We have a first order, and we have a second order. Now technically you could have a 1.5 order or okay, but at this point these are our standard orders, and we'll explain what that means in a moment. Now mathematically it would be rate equals constant K. All right, now I'm only going to put one reactant here. Let's just put A, and let's just say that at this point it is 0. It would have a 0 here. Okay, we'd have rate equals K, concentration of A, 1, rate equals K, concentration of A, 2. Now, in a nutshell, what this means here is that the concentration of A, anything we do, if we knew K and I wanted to find this guy, if I were to change my concentration, how would that affect the rate? Well, since it's zero order, if I were to take my concentration and double it from 0.1 to say to 0.2, any value to a zero order is just 1. Anything to the 0 powers is just your power or exponent. Any number to the 0 power is 1. Therefore, no matter what the concentration is, this value is going to equal 1, and your K is going to equal your rate. So if I were to graph this, and this is a unique graph for a 0 order, and I were to go concentration versus time, okay? Now, get a little more room here. And there are plenty of examples where this works, okay? What it means is, okay, is that as this thing proceeds, it proceeds at a straight line. The slope of this thing is K, and this is one situation where K also equals the rate. Change in concentration divided by change in time, that's slope. Okay, rate is equal to change in concentration over change in time. This is one unique situation where the rate does equal my K, and we'll see other examples in a moment of how that works. Okay. But you would have, as time proceeds, your rate does not change. A pretty common example of this, I think people tend to use, like digestion of alcohol by your liver. Your liver can only digest so much alcohol at such a pace. If you were to drink a lot or little, it does not matter. It just takes a certain amount of time. That rate proceeds on and on and on and on. If you drink more alcohol, your liver does not digest faster. Okay. So now, a way I look at this is that essentially zero order, there is no effect on rate. For this guy, it is sort of a 1-to-1 ratio. That's how I think of it. Where if I double my rate, let's go 2 times my concentration. If X represents your concentration, I double it to the first power, and your K value is constant, then your rate, okay, will be times 2 as well. If I were to then take my concentration, triple it, okay, to the first power, 3 to the first power is 3, therefore 3 times K equals 3 times my rate. It's a 1-to-1 ratio. You should be able to sort of understand that. Now, if I take, in this case, my rate, let's say concentration equals X, okay, and I tripled my I don't want to triple it, let's just say I double it again, okay, times 2, double it, and then this thing is going to get squared. 2 times 2 is 4, times your value of K means that your rate is going to be 4 times. Okay. So doubling caused a quadrupling, or a squaring. Okay, so in this case, if I multiply my concentration times 2 gives me a 4, times 3 gives me a, in this case, 9 times. Okay, so it's squared. Okay, there's a squaring relationship here. It's not a 1-to-1 ratio. Okay, it's squaring. So that is my rate, and this is the little PowerPoint page. Here it just sort of talks about how taking your concentrations and doubling them. Okay. Now, this is an example right here of a chemical reaction of just water production. Okay. Now, again, remember, our overall goal is to be able to create a mathematical relationship that will help predict the future. So if I know my K and I know my concentrations and I know my orders, I can figure out what my theoretical rate will be, initial rate. Okay. So that's the overall goal of this. First and foremost, you should be able to write out a rate law reaction for any equation, just in general. Okay, now I'm going to put a new one here. Let's just go with this being rate law. Okay, so if I have a reaction that is A plus B yields C, plus let's say D, okay, it doesn't really matter. I could have a 2 here, I could have a 3 here, I could have a 1 here, and let's have a 1 there. At this point, my rate law would equal my K, concentration of A, concentration of B, and these I cannot put in here right at this point. I could put in question mark or whatever. There's something there, I just don't know what it is. They are not the coefficients. Okay? Cannot say for sure that the coefficients. There's a chance it might be, but at this point we just can't say. We need actual experimental data for this to occur. Okay? Any reaction, you can write this out. Now I will say that if something is 0 order, sometimes they take it out. So if hypothetically, and we'll learn how, just a short moment, how to determine these orders, but if B happens to be 0 order, they might write it like this. Let's say B is 0 and A is 1. Rate equals K concentration of A to the first power. They might write that. Okay. Now, should be able to at least get this point where we can write out a rate law. Now, how do we determine your order? Okay. How do we determine order? All right, now in the PowerPoint, which you're free to go and look at, I have examples. There's a lot more writing, a lot more little stuff to write down, so I'm using the PowerPoint. Okay. This is a pretty typical example of how you might get information from an AP question to help you figure out the orders. So they're going to set up essentially a series of chemical experiments. Okay. So you're going to see experiment 1, experiment 2, experiment 3, all right? And they're going to show you concentrations of these things, and then the initial rates. Now, I will say watch the initial rate. This one doesn't say what they're tracking. But for this reaction, we have apparently some nitrogen monoxide, some chlorine. I have a rate law reaction written out here. They're not telling me what they're tracking. They're saying it's moles per liter per second, but they're not telling what they're tracking. They will often throw in the chemical they're tracking, and then they might ask you a question later on about something else relative to that rate. And I would call it a rate within the reaction. If Cl is being produced in experiment 1 at this rate, then what would be the rate of production of some other element in the chemical reaction? Just so you're aware. All right, so how does this work? Well, what you do in this PowerPoint is going to step it through it, okay, is you need to pick out certain experiments, okay? And you want to say, well, okay, between experiment 1 and experiment 2, note that the concentration of nitrogen monoxide does not change. But the concentration of the chloride, or chlorine in this case, chloride more likely, is doubling. So, and this PowerPoint will step it through here. Okay, now notice right here, it doubles. And notice that the rate doubles. Okay. So I like to draw an arrow and say, because which way it's doubling. It's doubling in this direction, and it's doubling in this direction. So I draw right on the paper, and this one's not doing anything. So any increase in rate is due to the chlorine. Therefore, a double and a double, a linear relationship, 1 to 1, okay, that is first order. So right now we can say without a shadow of doubt, the chlorine is first order. I would go back to my original equation, take the y out, put a 1 in there. Any increase of chlorine, I would assume or accept there to be a proportional change in rate, period. Sometimes the questions are laid out nicely, sometimes you got to do a little problem solving. All right, so that one's now first order. Next one, now we have to figure out, okay, what's the NO? Now I got to pick a different reaction. I'm going to pick, let's say, I can pick 1 and 3, okay, or 2 and 3. Now, if I were to pick 2 and 3, note that chlorine's changing. I don't like that. I want to have a relationship here where only change in rate is due to the NO. So I'm going to pick 1 and 3. That says, okay, 1 and 3, 1 to 3, the nitrogen monoxide doubles. The chlorine does nothing. So any change in rate now will be due to the change in concentration of these guys. Therefore, 1 to 3, it goes from 2.27 to 9.408. I would simply divide this one by 3 by 1 would give me 2. Divide 9.08 divided by 2.27 gives me 4. So a 2 to 4 ratio is a second order. There. Now I have my rate law. Very often this is my first question that might be involved on an AP exam. Okay? So that's the first step. Second step they want you to do is, okay, determine K, and they also want you to find the units on K. Moving along here. Okay? Not difficult, just something new, and as you do it once, we'll do a couple of them in class, and you will find this to be quite straightforward. If you are struggling with this, make sure you get help from me. It is not difficult. So if you're finding difficulties with it, it's because you've missed some time or you haven't focused. You need to look at it. You'll find it is very easy. Okay, whether it's K or even the units on K, very straightforward. Now, how do you determine K and its units? Well, because it's mathematical. Okay, we're doing just simple algebra here. Pick any one of the trials you'd like. Substitute the values of the concentrations and the rate into the rate law equation. So I'm going to pick, in case now I'll go back to my data, pick any one of these trials you want. substitute concentrations in for each of these individuals, and substitute the rate in for the rate. Okay, so in this case, I chose trial 1. Put 0.0125, of course, there's a 2 here, square it. 0.225 to the first. Okay. I have my rate associated with that particular reaction. Then I just square it, multiply, divide out, and get my K value, which is 0.645, and I have some units here. Liters squared over mole squared seconds. We'll talk about that in a moment because they will also ask for that. Again, not difficult to find. Just got to have a little practice, get used to working with it. Okay, just a little algebra, dividing. Now, this is the K. That K will stand true in this equation right here as long as temperature is held constant. Okay, it's temperature dependent. Okay. We'll use this K in a few different ways, but all right, so that's my K value. So now I have my K, I have my powers. I, at this point, could substitute any concentration in for either of these guys I like, and I can solve for the correlating rate. That's important. What is the rate if both of these are 0.225? If this is 0.225, what's my new rate? That's a pretty common question. Determine the orders, determine K, and then find a new rate with your data you have. All right, so where do the units come from? Okay. Well, keep in mind, as algebra says, this equal sign, both sides are equal. All right, now, this is rate, which is moles per liter per second. Okay, that's what happened after this particular reaction. This is nitrogen monoxide, moles per liter, squared, moles per liter to the first. All right. All I did was take these units here and divide them out to equal K. Then whatever these units are on your right-hand side or your left side equals K. So let's go through it again. K is what I'm looking for. This is moles per liter, and it's squared, so it's moles per liter, mole squared, liter squared. This is moles per liter. This is moles per liter per second. So I'm essentially dividing it out or canceling like things on both sides. So the moles cancels moles, liters cancels liters, or actually I canceled the other one, same thing. Moles cancels moles, liters cancels liters, and now I then take my moles squared, liters squared, divide them out to isolate K. Whatever units I have on this side equals this one. So when you divide them out, now I get, when you divide a fraction, you multiply by the reciprocal. Okay, so that's why it gets flipped over here. So liters goes on top, moles goes on bottom, and the second stays on the bottom. So it's liters squared, moles squared, divided by seconds equals K. One thing I will also point out, and this is important, is that there is what's called an overall rate, and I will, if I can put this thing right on here. Okay. Now, an overall rate is another question you might ask. What is the overall rate law? Order. All you do for that is you have your rate equals K, concentration of nitrogen monoxide squared, concentration of the chlorine to the first. You simply add these guys up. This thing is a third order overall. Okay? It's second order with respect to the nitrogen monoxide. It's first order with respect to the chlorine. It's third order overall. Now, I've just gone over a couple of examples of how this works. That's what these videos are for, just to expose you to it, take a look at it. To get good at it, you need to run through a couple of examples. Okay. Now here's a final example of how they might use this information. What would be the initial rate in experiment 4? This is one they did not give us, which has NO equaling M and Cl equaling M. So in this case, looking for a concentration for M. Apparently it's not there, but they're saying that the NO is 0.05 and the chlorine is 0.225. Okay, plug those values in, square it to the first, put your K in there, plug it in, and there you go. There's your new rate. Okay. Overall objective of science, create models that have predictive power. This is our model, and we want to be able to predict the future rate, initial rate. And we will stop there.